Hi, my name is Lauren Paulson, and today I will be demonstrating an experiment that will show you what drag forces are. Without taking into account drag forces, we might think that objects fall, like in this experiment on the moon, where no matter what mass the object is, they accelerate and therefore fall at the same speed. However, Earth has an atmosphere, and this atmosphere creates air resistance, which means objects, when they fall, they have to push against the air. Therefore, some objects do actually fall slower or quicker than others. For my experiment, I had a friend drop a paper ball while I recorded. The paper ball will catch some of the air and therefore demonstrate this air resistance. The physics principles this lab covers are velocity, acceleration, force, gravity, and drag. After performing my experiments, I put it into Tracker and plotted it. I then made a model of my experiment on GlowScript. I changed the radius of the ball, some of the visualization. I added a second graph for velocity. I changed the mass, so the mass was the mass of my piece of paper. I put in gravity. I then also calculated the force using the mass times gravity. Now, this being the force means that this model did not take into account any drag forces. So this would be like if I was dropping this in a vacuum, like in that experiment on the moon. As you can see, the velocity has a constant slope, which means this assumes there's a constant acceleration of 9.8. I then made a second model which took into account the drag force. This one had a proportionality constant for the magnitude of the drag force, which I labeled B, and then I would calculate the net force based on what this drag constant was. So this one took into account the drag force. You can see that the ball in this model dropped much slower, as well as the velocity graph did not have a constant slope. So what do these velocity over time graphs mean? The first velocity over time graph of the model without any drag forces demonstrates the acceleration. The slope of this velocity over time graph is going to be 9.8, aka little g, or Earth's gravitational constant of acceleration. The second velocity over time graph for the model that had drag represents the change in velocity as acceleration acts on it, but also as drag acts on it. It also, from this model, we can see what the terminal velocity would be. This is where the drag force and the acceleration are equal, therefore the velocity stays the same and is not changing. Now, this terminal velocity on this graph would be where this graph starts to asymptotically reach, so where the asymptote of the horizontal graph would be. I then took my data from both of my GlowScript models as well as my tracker data and then plotted these on a graph in Excel to compare them. The blue line represents my model without any drag forces. As we can see in this model, the ball fell much faster than the other two. This is because the ball had no drag forces that were pushing up on it. The orange line, my model that represented drag, and my gray line, my tracker data, are quite similar, but for some reason my tracker data has more of a straight line while my GlowScript data is more curved. My theory as to why my tracker data is more straight than the GlowScript model with drag is because my tracker data may have hit terminal velocity quicker than my GlowScript model intended it to, this causing the tracker data to get straighter much quicker than the GlowScript model. The tracker data also has small bumps in the data. This is likely due to my camera slightly shaking or small imprecisions while tracking in the tracker app. How would the terminal velocity be different if instead of being dropped, an object was thrown downwards with an initial velocity? I don't think it would matter whether the ball was dropped from rest or thrown down with an initial velocity. This is because terminal velocity occurs when the ball's downwards force, the force of gravity, which is constant, is equal to the force's force of drag, which is a constant times the ball's velocity. Now, this velocity can happen at any point, whether it is when it starts or when it accumulates that velocity. Therefore, the terminal velocity will be the same. We can see this in the GlowScript model I made, where the ball has an initial downwards velocity. Thank you so much for watching, and I hope you were able to learn something about drag forces.